components of the velocity vector, whether it be in any coordinate system, alone is non-zero. So now we will go to the next case where two of the velocity components are non-zero. We consider a special case of what may be roughly labeled as a planar flow. So by planar flow I mean the two components that are non-zero. They are dependent on the two coordinates associated with the two components. For instance, if I consider the Cartesian V1 and V2 not equal to 0, by planar flow we mean that V1 is a function of x1 and x2 and V2 is a function of also x1 and x2. Whichever components are non-zero, they are dependent only on those coordinates associated with that component. For instance, spherical polar is to be VR, a function of r and theta, and then V theta is a function of r and theta alone. They are independent of phi. V phi is 0. Right? So that is what we can call as planar flow. So this is certainly slightly more complicated, certainly situation than what we have been considering so far, where only one of the velocity components is non-zero. Towards handling this, we derive what is called as a vorticity equation. Vorticity equation is derived by first considering the form for the acceleration, which is given by this. The vorticity equation, what you have to remember about the vorticity equation is you have to take the curl of this equation. Right? So towards that, I will write 2 or 3 important identities that we would use, which we have already sort of proved in the assignment. Go back to the assignment 1 probably. It gave a whole set of identities to prove. We have used the vector A and now writing it for the velocity vector, and also this is the first identity that we would use. Other identities are the fact the curl of the gradient of V dot P, right, is 0. The gradient of a scalar is 0. We can prove it for any scalar. The curl of the gradient of a scalar is actually the 0 vector. And here, for the scalar, I am substituting the quantity V dotted with V, which is also a scalar. Right? The third identity has to do with the curl of the cross product of two vectors, which can be shown to be, I don't know if we actually prove this, but we can prove this. So, we haven't proved this before. You can easily attempt to prove this with all the familiarity with the epsilons and so on. So, we are not going to prove it now. Leave it as an exercise. And then the fourth one is that the divergence of the curl of a vector is 0. This has not been proved before, because you can easily find in Aris 324.4. I'm taking that identity from that. So let's now take the curl of this expression for the acceleration and use those identities to quickly get to, I'm going to take the curl is taken of a vector. This is a vector equation. I'm going to take the curl of the vector. So what I get is that the curl of the acceleration is given simply by the curl of here I'm going to substitute for V dotted with the gradient. So the curl of that. Now, first thing is you can easily show that the curl of this is actually equal to V by dE. That can be easily shown. I'm not going to prove that. Basically, the curl involves, it's a vector operator. It involves a gradient, and it's like a differentiation with respect to x1, x2, and x3. So there is a partial derivative with respect to time. It's a another partial derivative with respect to time. So basically, what it means involves is the interchange of the order of differentiation of partial derivation. That's what is involved. Right? We know this in the case of a single scalar spatial operator involving the derivative with respect to x1, x2, and x3. So if you apply that repeatedly, you will get this very easily. Now, with respect to that, since V dotted with is given by that, so what I have is the curl of this vector here. The curl of is equal to the curl of, right, half times the gradient of V dotted with V. Plus or rather minus V dotted with V the cross product with too many of these cross products. So I'm not going to define the vorticity vector W. This has been distinguished from the omega. We saw the angular velocity, right, associated with the rotational motion. Look at the velocity gradient tensor. It can be split into two parts. The antisymmetric part will correspond to rotational motion. Symmetric part is what we call as a deformation tensor. We could associate, so that leads to the antisymmetric part can be associated with the rotational motion, which we said has a scalar omega, which is the angular speed. The vector omega, which is the angular velocity vector, which is the angular velocity, angular speed multiplied by the unit vector corresponding to the axis of rotation, and then it can be expressed also as an antisymmetric tensor. So for the velocity gradient tensor, the angular velocity vector is shown to be half times the curl of the velocity vector. We have already shown it. But here I am going to use a W, but this is consistent with the notation used by Aris and Lightfoot. It doesn't have that half, right? And it's simply the curl of the velocity vector. This can be called as a vorticity vector. Half of that will give the angular velocity associated with the rotation, right? So with this, I can. So now this is actually equal to 0 because this is the curl of the gradient. So this is equal to 0. So this then is equal to the curl of the cross product of the velocity times the vorticity vector. Right? So I may now write the curl of the acceleration as the curl of the partial derivative with respect to the velocity time plus or rather minus, I may make it also plus by simply interchanging the order of this cross product, and I can write this as the curl of. Here I am going to use the third of the expressions I have written there. So if I take the curl of what is the vector times the velocity, then W is equal to A and V is equal to B. V, what do I get? Right? So that's what I'm going to use. So that would be the divergence of the velocity times the vorticity vector. Right? V is for us V and A is W minus blindly applying that identity for the case where A is equal to W and B is equal to B plus B dotted with plus or rather minus A, which is immediately see that the divergence of W is actually 0 because when I put, thankfully I put W to be A there, so if I put this, if I use this, right, that is 0. I'm sorry, if I use this is for any vector, right, so if I put B here, A is equal to B, so if I use this here, then the divergence of the vorticity is clearly 0, right? So you cannot consider the A and B in one expression with another, right? So clearly the divergence of this term is 0, right? Probably I cannot get rid of anything else, right? So what I am going to get here is this is what I have got. There's no need to have done this. So we could probably just write this as no need. This is of course true, but I could just leave it as it is. Oh, I'm sorry. This is can be written as dw by dt, right? So of course I need to do that. So what I have is the curl of this is d by dt of the curl of B. I can interchange the two derivative operators, and so this is by definition W. So I get this. So now I can combine these two, right? So this is d by dt, the partial derivative, plus B dotted with the gradient. So what can I replace it by? The substantial derivative of the vorticity vector, right? So this is equal to dw by dt plus, oh that I have done, plus it may not get done, right? So all you have to remember is that there's nothing. So far it was no laws of fluid mechanics. It's just the formula for the substantial derivative, right? And I've introduced a new quantity called the vorticity vector, which is the curl of the velocity vector. And I've used some vector identities that are applied for any vector or scalar or whatever, right? So nothing has been used so far as far as fluid mechanics is concerned. Now I'm going to make the first use of the equation of fluid mechanics. Since I see the divergence of the velocity vector field, I'm going to use the continuity equation. And I'm going to use it in the following form, that d rho by dt, substantial derivative of the density, plus rho times the divergence is equal to 0. Right? So now I am going to replace the divergence of the velocity simply by minus 1 over rho d rho by dt. Right. So now what I get is that the curve of the acceleration is equal to substantial derivative of the vorticity, right, minus this other term I will write here, plus, or rather minus 1 over rho d rho by dt times w. I should have written that there. Right? So now if I look at this, so this involves dw by dt. So I can now let us say now, see, this involves, and I also get a rho here, right? I can get a rho, I can multiply rho by rho, possibly. That's not going to, yeah, some sign talking possibly. These two, but I have a negative sign. Yeah, that should not be a problem. There's no need to multiply. Actually, it's fine. Right. So what I actually do is you would have to calculate the d by dt of w by rho. Right. So if I do that, then there should be no problem. And I can account for the minus. What I am looking for is not rho times w, but rather 1 over rho times w. Let's just look at this, right? So now this is a substantial derivative, is just like any other partial derivative, only that whatever is being differentiated is expressed in terms of psi, material coordinates and time, right? So the common rules of differentiation apply. So clearly this can be written as 1 over rho dw by dt, right, plus w times, that's a vector, times d by dt of 1 over rho, which will be minus 1 over rho squared d rho by dt. So actually what I need is actually divide rho by rho. So if I now divide rho by rho, right? So I can now combine 1 over rho dw by dt minus 1 over rho squared here. So I can combine these two terms now as they appear there, and I can write it as d by dt of the vorticity vector divided by rho. What I would get is 1 over rho times the curl of the acceleration is given by d by dt of minus this is what may be called as the, or often referred to as the Beltrami diffusion equation. This is the terminology used by Seven. This is a very important relation. And actually, the way we got to it is somewhat long-winded, but all you have to remember is that this is the starting point. Everything else is just manipulation using some well-known vector identities and definition of this very important quantity, the vorticity vector. finally we have used the continuity equation. So the final result, what we are going to take. All I wanted to show was that this is well within the reach of any of you who are comfortable with using these vector and tensor identities. There's nothing. What is the use of this? Why did we take so much time to derive this? We now see the use of this, right? And its application to the planar flow. So as an example, first I will take the the quantum acceleration. Now going in, we've already used the continuity equation. We now use the equation of motion. And what we are going to do in the equation of motion is not apply the general equation of motion, the equation of motion for a linearly viscous incompressible fluid. For such a fluid, now I'm going to specify everything until now, right, is the most general, uses the expression for the substantial derivative of the velocity. All I've used is the continuity equation in its most general form. We have not applied the fact that the fluid, what is the nature of the fluid, we have not taken into account. So it applies for compressible as well as incompressible fluids, right? And for linearly viscous or not, it doesn't matter, right? All we have used is the continuity equation. So this equation is very general. Now I am going to specialize to an incompressible linearly viscous fluid, for which, as we have seen, the continuity or the equation of motion can be written as minus the gradient of the pressure plus rho times the body force plus the viscosity times the Laplacian of the velocity vector phi, right? So here what I will, so now I can divide by rho and I can make this the kinematic viscosity rather than the dynamic viscosity. Simply the dynamic viscosity divided by the density, right? So that is what I have. So now, since I can now write this as the gradient, so I am now going to assume that the body forces are, so now we see that this is the equation of motion for a linearly viscous incompressible fluid. Now I am going to assume the body forces are conservative, which means that V can be expressed as the gradient of some potential which we may call as some phi. That is a conservative potential. Conservative force means that the force can be expressed as the gradient of the potential. Right? Now the form of that, either you put it as minus the gradient or plus gradient, doesn't matter. It's still the gradient of minus phi. I'm putting it as minus phi just so that I can combine it with this, and so this would be the gradient of P over rho, or minus the gradient of P over rho plus phi, plus this. So you see why I make this simplifying assumption. So as we simplify the equation, we are going to consider only the gravity force, which is certainly can be shown to be a conservative force, right? Yes.
Is it? We have taken the negative of gradient to conform with the physical observation that all the conserved quantities go down.
That is not. Potential can be anything. You can define it based on the particular situation. What the potential is, it will depend on whether I express it as minus the gradient or plus the gradient. That is totally immediate, right? So let's not get into that. So I have this. Now I take the cross product of this, and the curl of this now, right? The curl of this. Again, I make use of the fact the curl of the gradient of a scalar is 0. That's the reason why I am making the simplifying assumption, right? Otherwise, the equation will become more complicated. So, if we are anyway not going to consider body forces in great detail, and the body forces that we are going to consider in the course are conservative, right? So, it's not such a a restrictive assumption, right? So if I take the curl of this, then I will get the curl of the acceleration is equal to simply the curl of the Laplacian, right? And it's also possible to show that I am going to leave this as a Cartesian coordinate. You can very easily show that the curl of the Laplacian is equal to the Laplacian of the curl. Again, it's because the Laplacian deals with spatial second order derivative. The curl is a vector operator, so cross product. This also effectively involves differentiation with respect to the space one-time differentiation. So it's not surprising that the operations can be interchanged, but you can prove it more rigorously, right? So clearly, then this is the Laplacian of the vorticity vector, right? So we get this triangle relation for linearly viscous incompressible fluid. The curl of the acceleration, right, is simply given by the kinematic viscosity times the Laplacian of the vorticity vector. Of course, under the further simplifying assumption, the body force is a conservative force. All those approximations are inherent in this. Now, let us apply this, which is a general equation. So, we are going to consider an incompressible fluid, right? Because this is valid for compressible as well as incompressible fluid. For an incompressible fluid, the row here is outside, but for an incompressible fluid, this row can be taken out, and this row can also be taken out of the deck. I mean, this row is outside as it is, so it can be taken out here, and so I can cancel the row. This is now ultimately diffusion for an incompressible fluid. And now I'll combine these two. So the curl of the acceleration is given by this, so I will get dw by dt, right? Minus, this is why that equation is called as probably a Beltrami diffusion equation. It's not very clear why, what is about diffusion that comes out of that. But clearly you can see here, you all read out the fixed second law of diffusion, which involves the Laplacian of the concentration, which is why this may be called as a diffusion equation. So it effectively can be regarded as representing an equation for the diffusion of vorticity vector, right? So is equal to this can further be simplified if I want to bring in the partial derivative. So this can be written as dw by dt plus d dotted with minus w dotted with gradient of the velocity is equal to now we will see the relevance of this to the particular example that we said we are going to consider for two-dimensional flow. We can call it the two of the velocity components are non-zero. We're considering again only the planar flow. Now the idea of deriving this is that this is nothing but the equation, of course, combined with the continuity equation for incompressible fluid is just the density is constant, right? So this can be effectively regarded as another way of writing the equation of motion for the linearly viscous incompressible fluid, but it is not entirely in terms of the vorticity alone. In its general form, it's not quite useful, because you might think that we have now replaced the velocity as a variable with the vorticity, but that's not quite true, because both of them are there. So really no great simplification has been obtained so far, right? The relevance of this is to the way the equation of motion reduces to the particular case of the planar flow, and as always I will consider the plane of Cartesian coordinate first and see what is the result of this, right? So we now consider V1 equal to V1 of x1, x2. Right? So since the curl of the vorticity vector appears, we have to ask what is the curl of the velocity vector for this particular case. Now you will see why that equation is in some cases, in some sense, necessary. So now the curl of the velocity, right? If I look at this, it can be written as E epsilon ija. Just in case you thought that you're done with the epsilon ijk, it comes to contours of range. So what is this? B K comma J E I. Right. So let's now calculate what is the vorticity vector, curl of the velocity vector. The first component, right, would be, so this is Wi is epsilon I J K B K comma J. That's what I am looking at, right? So now you can very clearly see that what would be W1? W1 would be for I equal to 1, right? So this would be epsilon 1, 2, 3, right? B3 comma 2, which is epsilon 1, 3, 2, B2 comma 3. So what is the value of this?
B32 minus what? B2.
Let me finally further. I don't even want to look at it.
Sigma capital.
No, for this particular case, what is it? 0, right? Because B3 is 0. So this is 0. B2 doesn't depend on x3. So this is 0. The same way, you can easily show that W2 will also be 0. Right? W2 is epsilon 2, 1, 3, let's say, right? B3 comma 1 plus epsilon 2, 3, 1, B1 comma 3. Again, that is 0. For different reasons, right? One is B3 is 0 because I'm considering a planar flow with B1 and B2 alone present. And finally, secondly, B1 is independent of x3. Because of that is 0, because W3 will not be 0, right? So now look at the components of, we can look at it here, right? So W1, so what will it look like? So first equation would be, so I write it for dW1 by dt, right? Minus 1, I'm getting component by component, right, is equal to 1. And similarly, dW2 by dt So I have effectively proved W1 and W2 are 0. These two are 0, so you would expect that the other two must also be 0. By W dot, the first component of that, and the second component of that, you would expect to be 0. This equation actually has to be satisfied. You can easily verify what is I, if I want to write it, right, for instance, would be Wj, right, Wj Aj, that would be Bi comma J, right, the gradient of velocity is Ji component would be Bi comma J, so this is the ith component of this, right, so now let's take the first component. right? So it has to be summed over all three. But I know that W1 and W2 are 0, so those terms I don't have to consider. So I will consider only the third component, W3, V1 comma 3, which is clearly 0 because V1 comma 3 is 0. That's also 0. So you can easily show in the same way that you verify that, right? But what is interesting is let's look at the third component. What can you say about this? That's also 0, right? Because of the third equation, let's look at the third equation. Third equation, we know that this is not 0. Clearly it won't be 0. What is W3? Right? W3 is 3, let's say V2, 1, right? V1 comma 2 plus epsilon 3, 1, 2, V2 comma 1, 3, 2, 1, right? So this would be 3, 1, 2 is positive 1, right? So this would be dV2 by dx1 minus dV1 by dx2. Certainly, I'll assume the planar flow, so we cannot, generally it will not be 0, right? So, when I look at the third component, the third component would be, the third component is this, right? The third component is this, W3, right? And certainly, now what we are getting is that since I've just shown that this will also be 0, and this will be W1. The first two terms, J equal to 1 and 2, they are 0 because W1 and W2 are 0. The third one, W3, involves V3, right? V3 is itself 0, right? Identically. So anything being connected with V3 will also be 0, so this is also 0. So I am getting for the third component. So two of the component. This is the advantage of writing the equation in terms of the vorticity. Its advantage is particularly in the context of the planar flow. Because what happens otherwise, if we write the equation of motion, right, we have to consider two of the components because V1 and V2 are both non-zero. However, when we write it in terms of the vorticity, the advantage you get is that two of the components equation simply becomes 0 equal to 0. All the terms vanish. And the third, the one which involves W3, the vorticity, third component of the vorticity vector will give rise to
What term?
this is also 0. So simply dW3 by dt is equal to, we get this. But that's not all. Right? Note for further utility of this equation, we have to introduce now what is called as what we will finally get is a combination of the vorticity equation and the concept of the stream function, which I am going to introduce. Both vorticity equation is very general, we have seen, right? Anything involving the vorticity, but it gives considerably simplified equations when you go to the planar flow, right? And it leads finally to this. But to further proceed, because if you further simplify this, we still are left with, we still get the velocity. I'm not very sure whether, what happens to, because this is just a substantial derivative. We want to reduce it to partial derivative. Again, I get another velocity component, right? We don't know what will happen to that term anyway. But before we proceed further, I will introduce the idea of stream function. When it is combined with this, it leads to a different representation of the equation of motion. Now, the stream function also has its utility within the context of planar flows only, right? So, the stream function definition relies on the following feature of the planar flow, is that if you write the continuity equation, right? Any kind of planar flow in any coordinate system you consider, there are three terms in the continuity equation for the incompressible flow. The continuity equation, the incompressible flow is simply the divergence of the velocity field is zero. Now you take any of the three coordinate systems you have considered, you will get three terms, right, for the divergence. Now, for the planar flow, whether you consider a planar flow in Cartesian coordinates are spherical or cylindrical, you will one of the terms would simply vanish. So this is where the stream function concept applies. So for the continuity equation in the Cartesian coordinate will be this. Now the stream function is defined in such a way that the continuity equation is satisfied, and one way of defining it, there are many equivalent ways, but I will choose the one that I have taken up here just to be consistent. It defines psi is defined in such a way, psi is a function of x1 and x2, defined in such a way that d1 is equal to d psi by minus d psi by dx2, and d2 is equal to d psi by dx1. Right? I can always introduce. Suppose I introduce what is the utility of this, right? So this is what you have to see. Now, if I introduce it in this way, right? So dv1 by dx1 can be written as minus d square psi by dx1 dx2. dv2 by dx2 is d square psi by dx2 dx1 is clearly zero. This is the motivation behind the definition of the stream function. Similar stream functions are definable for cylindrical and spherical polar coordinate systems where two of the terms only are present. Right? So this is clearly a very straightforward way of defining the stream function for Cartesian coordinates. Of course, we could have also defined d1 as d psi by dx2 and d2 as minus d psi by dx1. So this is what is the definition, right? So now we can see what happens to W3. W3 becomes d by dx1 on d2, which is d psi by dx1 minus d by dx2 of d1, right, which is minus d psi by dx2. Which is nothing but d squared by dx1 squared psi is d squared by dx2 squared psi, which in the case of the planar flow can be simply written as the Laplacian of psi. Right, so you have to look at whatever we have derived so far in combination with the stream function. This is what leads to. This is basically an attempt to simplify the solution of the equation of motion for planar flow. Right? Now, many people would argue that in the modern context, the stream function doesn't have as much utility, where these problems can be numerical solution very easily possible without even looking at the stream function. The stream function is an important concept because for planar flow, the equation psi of x1, x2 equal to a constant also gives what are known as streamlines, which are very important ideas, which unfortunately we have not introduced so far, but anyway I introduce it shortly. Right? So this is what we have. So W3 is actually Laplacian of psi, which means the Laplacian of W3 can be written as The Laplacian of the Laplacian of psi is often denoted by the gradient operator raised to the power 4. So it is simply Laplacian acting on the Laplacian. Now we have to look at what happens to this because we've run out of time today. We will take it up in tomorrow's class. So those who have time for questions can stay back. Tomorrow I will also announce the seating arrangement which may be slightly modified from what we had last time for quiz 2. Right? And we will briefly discuss about what you should